everyone. Today we're going to talk about radiation and half-life and how to measure those things in atoms. First thing we need to talk about with radiation is understanding where it comes from. Now, I think a lot of us, when we think about radiation, we think about science fiction movies and superheroes and superpowers, but the reality of that is that most of our radiative energy on our planet comes from our sun, and it is radiated out from the ground. Today we're going to talk a lot more about radiation in the form of particles that come off of certain metals. Some of the things that Becquerel and the Curie showed us when they discovered radiation. Okay. First thing we're going to talk about is we're going to revisit isotopes. Isotope is a naturally occurring variance of an element. Now, one of the ones that I always talk about is hydrogen. Hydrogen has three types. It has protium, deuterium, and tritium. They're all hydrogen because they have one proton. But protium has 0 neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. And each one of those particles, each one of those atoms, has a certain amount of energy that it can expel when it is giving off any radiative energy. Okay, another example we can talk about is uranium-238. When it comes out of the ground, that's what we find. When we process uranium at uranium-235, then that's what we use for nuclear power. Okay, but they're both uranium because they have 92 protons. All right. Now, our three main types of particles that we're going to talk about are alpha, beta, and gamma particles. Now, this is all a direct result of the work from Becquerel and the Curies and their study of things like uranium and radium. And we use alpha, beta, and gamma to show where this energy comes from and how it is formed. Alpha, beta, and gamma are the first three letters of the Greek alphabet. So do make sure that you know these three symbols and how to recognize them. Okay. This is called the uranium disintegration series, or the uranium decay series. And a lot of times it is used to show how alpha and beta particles will change an atom into something else. Okay, and in more detail, it shows every single step of how uranium becomes a stable atom. Uranium starts radioactive, and it will go all through all these steps at about 4.5 billion years to become lead when it's stable. Incidentally, most everything after lead on the periodic table is radioactive. And trying to get rid of particles, get rid of neutrons and get rid of protons and electrons in order to become a stable atom is what radioactivity is unstable nuclei are expelling off particles to become stable. All right, so let's look at each of these particles. Alpha particles are essentially the same thing as a helium nucleus, 2 protons and 2 neutrons, but it has no electrons, which means 2 protons would give it a positive charge. Alpha particles are what Rutherford used in his gold foil experiment. Okay, now the example I've given you here is radium decaying into radon. Radium with a mass number of 226 will decay into radon-222. It loses 4 particles. It loses 2 protons and 2 neutrons. 88 protons to 86 protons, 138 neutrons to 136 neutrons. Okay, so it's important to know that those 4 particles are an entire alpha particle. Okay, now alpha particles are relatively weak. They can be stopped by paper. Okay, your skin is thick enough to stop alpha particles, and alpha particles are all over the place. Okay, and they're not necessarily dangerous because, like I said, you can stop them. Your epidermis is thick enough to stop them. All right. Next, we have beta particles. Beta particles are essentially an electron. Now, where we get beta particles is when a neutron turns into a proton. So if you look here, I've got carbon 14 and nitrogen 14. My number of particles did not change. What does change is the types inside. a neutron turns into a proton. So 8 neutrons become 7, 6 protons become 7. Okay, that process of turning a neutron into a proton expels an electron of energy. Now, beta particles, they're a little stronger than alpha particles, but they are still relatively weak. Tinfoil or aluminum foil can stop beta particles. Okay, they can penetrate your skin, but they can't penetrate too far into your body. All right. So next is gamma particles, gamma radiation. And gamma radiation is extremely high powerful energy. Okay. Now, the reason why it's so high powerful, I'll show you in a second. But if you look at this, I've got 10 protons turns to 10 protons, 10 neutrons turns to 10 neutrons, and that's the same. Well, what happens is we have electrons in an excited state to electrons of a lowest energy state. If you remember, Niels Bohr showed us how electrons can change different energy levels. And in an unstable atom, those electrons will fall down to a lower energy level, and in doing so, it gives off this really high level energy that we call gamma radiation. Now, it is not visible. You can't see it, okay? But gamma radiation is very powerful. It is so powerful that it takes feet of concrete or feet of lead to stop it. Your skin won't stop it, okay? Paper won't stop it. It takes feet of concrete. Now, why? If you remember the electromagnetic spectrum, the visible light spectrum right here in the middle, the Roy G. Biv, what you can see, the reason why you can see it is because of the size of those wavelengths, you know, at the 100 to 500 nanometer level. Those wavelengths are just the right size that they can enter your pupil and interact with the rods and cones of your retina, so you can interpret those signals. Well, if you go bigger, like infrared, I know you've seen movies or like military equipment that shows heat signature of human bodies. We can't see that with our own eyes. We have to use specialized equipment because infrared signatures have a larger wavelength. We can't see that. Radio waves are, some of them are as long as a football field. We can't see that, but that's why your car has long antenna, or why your cell phone has antenna, because it has to be really long to catch radio waves. Well, if we start going smaller, ultraviolet radiation is small enough that it interacts with your skin cells. Okay, ultraviolet radiation will burn you. Okay, it will burn you because it interacts with your skin cells. X-rays, I think we all know what X-rays do. X-rays can penetrate through your flesh and your tissue, but it can't penetrate through the density of bone. Okay, and then comes gamma rays. Gamma rays are so small they can interact at the atomic level. Okay, they can kill DNA. So that's why it takes feet and feet and feet of concrete to stop gamma radiation. So on Earth, the way we stop ultraviolet radiation, we have our ozone layer. Okay, but we still have lots of radiation that comes off of the sun. Like I said, we have a lot of radiative energy. There are gamma rays that come off of our sun, and we have an invisible force field surrounding our planet called the magnetosphere. And if we didn't have that, all that gamma radiation would actually enter our atmosphere and bake our planet. There wouldn't be any living cells that would survive on our planet's surface. That magnetosphere is a huge force field for us, but you can see it sometimes. If you've ever seen pictures or videos of the aurora borealis, that's because that gamma radiation is being pulled into the poles at the magnetosphere, and it's interacting with the ions in our atmosphere. And it's relatively harmless, but that is radiation entering our planet, which is pretty impressive to be able to see. Now, what is all this for? Well, we use it to measure something called half-life. Half-life is the amount of time it takes for half of the particles to decay or to become stable. So in the uranium disintegration series, going from uranium to lead, half of the particles do that. Half of the particles become lead. And then it takes another 4.5 billion years for another half to become lead. And then another 4.5 billion for another 4.5 to become lead. And it goes on and on and on. So let's look at a smaller example. We got 20,000 atoms. And its half-life is 1 hour. After 1 hour, how many atoms will be present? 10,000. After 2 hours, how many would be present? Another half would be 5,000. After 3 hours, 3 half-lives, how many would be present? Another half would be 2,500, and so forth. So you can use these as fractions as well. So half would be 50%, a fourth would be 25%, and so on. Now, what if you have a situation where you're calling for 15 half-lives? You're not just going to go divide by 2, divide by 2, divide by 2, divide by 2. I guess you could, but you'd probably mess up. So you can use these equations right here to help you out with those numbers. So if I take my original question here with 20,000 atoms and 3 half-lives, 20,000 atoms and 2 to the third half-lives. Well, 2 to the third is 8. 2 times 2 times 2. 20,000 divided by 8 gives me 2,500. Okay? If I had a million atoms and I had 10 half-lives, it would be a million atoms divided by 2 to the 10th. Okay? So you can also use this as a fraction. What if it said, what fraction of your substance would remain after 10 half-lives? Well, it would just be 1 over 2 to the 10th. Okay, so you can use these two equations here to help you out with really large calculations or large amounts of half-life times. Okay? Other than that, that's about it. Okay? Next unit, we're going to be talking about periodic trends and electron configuration. But until then, remember, work together, help each other, and make the world a better place. See ya.